Hello students, welcome back to MKG Online Study and E-Learning Platform. Videos 1 to 11 were our foundation. We talked about how hardware thinks, how clocks work, how events happen, how always work, blocking and non-blocking assignment, assign, wire, rich, if else, and finally the case statement. But now we officially enter Unit 1. And I want to start Unit 1 with a very simple question. Imagine I give you the circuit. I don't give you a software program. I don't give you a Python script. I give you an actual digital circuit. And I ask, can you tell a computer what this hardware is? Think about that for a second. How would you do it? How could draw it? But what if the circuit contains 1000 gates, 10,000 gates, a million gates? Now drawing everything manually becomes ridiculous. So engineers needed something better, and that is where HDL enters the picture. Today we are going to understand what Verilog actually is, and trust me, by the end of this video, I don't want you to simply remember Verilog is a hardware description language. I want you to understand why that statement exists in the first place. Let's start from hardware. Forget Verilog for a moment. Forget syntax. Forget programming. Imagine I am standing in front of your classroom and I draw a small digital circuit on the board. And I ask, what is this? You look at it and say, ma'am, that's an AND gate. Correct. Now I ask, can you describe this circuit using text? And suddenly silence. Because we are used to think about hardware usually. We draw inputs, gates, outputs. But computer and design tools need a formal way to understand that design. That's the problem we are solving. And that's why we need a hardware description language, HDL. Let's take the simplest possible example. We have two inputs, A and B, and an AND gate. They go to the AND gate and we get an output. A is 1 and B is 1. Y becomes 1 and otherwise Y becomes 0. Simple. And here is my question for you. Can we describe by using this text? Not a drawing, not a photograph, not a schematic. Text. That's exactly the problem Verilog help us solve. And here is where the story gets
HDL, Hardware Description Language. Pretty straightforward, but don't just memorize the expansion, understand the word hardware. We are talking about digital circuits description. We are describing what that hardware looks like or how it behaves. Language. We are using a formal language that design tools can understand. So an HDL allows us to describe digital hardware. And Verilog is one such HDL. And now students often make a mistake here. They hear the word language and immediately think, oh, programming language? Not so fast. That's our next concept. Programming language versus HDL. Think about Python. You write something like x equals to 10, y equals to 20, z equals to x plus y. The processor executes instructions. There is a sequence of operations, but HDL is different. Let's make this distinction very simple. Programming language, instruction to execute. HDL, description of hardware. That's a huge mindset shift. And this is probably one of the most important things you will learn in this entire Verilog course. Because if you approach Verilog like Python, you are going to get confused. If you approach Verilog like C, you are going to get confused. You need to ask, what hardware is my code describing? Not merely what line execute first. And that's why our previous 11 videos were so important. We are training your brain to think like hardware. Why do we need Verilog? Okay, let's create the problem. Suppose I ask you to design one AND gate. Easy. You draw it, done. Now I say design 1000 gate. Still possible, but imagine 10,000 gates or 1 million gates manually is impractical. Would you draw every single gate manually? Absolutely not. That would be insane. And modern processor and chip contain enormous amounts of digital logic. So engineers need a scalable way to describe the design instead of drawing every single piece manually. And we can describe the hardware using a language. And that language can then be processed by electronic design automation tools. That's the power of HDL. So, what exactly does Verilog allow us to describe? I want to remember three words: structure, behavior, connections. Let's understand each. Structure. What hardware components exist? Maybe a multiplexer, AND gate, register, counter, decoder. Behavior. What should the hardware do? For example, if select is 0, choose A. If select is 1, choose B. Connection. How are components connected? Maybe input, multiplexer, register, output. So, when you are reading Verilog, don't just look for keyword. Ask what hardware exists, what does it do, how is it connected. That's how an RTL engineer reads code. Now let's zoom out. Where does Verilog actually fit into the engineering process? Think of Verilog as a blueprint. If you are building a house, you don't start by randomly putting bricks. You first create a design. The blueprint describes what you are going to build. Similarly, Verilog describes the digital hardware we are trying to create. So conceptually, Verilog describes the intended hardware. Tools process the description, analyze and process the description. Synthesis, create an implementable digital hardware structure. And eventually that hardware can target an FPGA or ASIC hardware. This is the first big picture you should have in your head. Three ways of thinking. Now I am going to give you a habit and I want you to use this habit for every Verilog program from now on. Whenever you see Verilog, ask yourself three questions. What hardware exists? First one, what hardware exists? Maybe it is a multiplexer, AND gate, register, counter. Second, what does it do? For example, select A when select equals to 0, select 0 when A. Third, how it is connected, how is everything connected? Input, logic, output. If you develop this habit, if you remember this thing, if you develop this habit in thinking three ways, what hardware exists, what does it do, how is it connected, you will start becoming someone who can read RTL. You will stop being someone who simply memorized Verilog syntax. And that's a much bigger skill. Let's practice that first question. Suppose I say, design a circuit that selects one of the two inputs. A mux. Good. Suppose I say, store a value on the rising edge of the clock. What hardware? A resistor. Suppose I say, perform logical AND. What hardware? An AND gate. Suppose I say, count clock pulse. What hardware? A counter. See what's happening before writing Verilog. You are already thinking in hardware. That's exactly what I want. Now question number 2. What does the hardware do? What does the hardware do? You have to describe the intended relationship between inputs and outputs. Let's take a mux. Imagine two inputs A, B and one select signal. If select equals to 0, we want Y equals to A. If select equals to 1, we want Y equals to B. That's the behavior. Only after we understand that behavior do we ask, how do I express this in Verilog? This order is important. Hardware idea first, Verilog syntax second, not the other way round. Third question, how is it connected? How is the hardware connected? Input, logic, output. For a more complicated design, input, multiplexer, ALU, register, output. This is how digital designer think. They don't see a wall of Verilog text. They see blocks, they see signals, they see connections, and eventually they see the hardware that the code represents. Now let's address the elephant in the room. You will look at Verilog and think, wait, this look like programming. Yes, you will see. If case always operators, variables, and you will think this is basically C. No, the syntax may look similar, but the underlying model is different. Imagine two people speaking English. One person is giving instruction to a worker, the other is describing how a machine should be built. Same language style, completely different purpose. That's the difference in software instruction executes. In HDL, hardware is described. And this difference becomes even more obvious when we talk about concurrency, which, by the way, we have already introduced in our foundation videos. Okay, enough theory. Let's write our first proper Verilog example. Look at this module and gate. Input A, input B, output Y. Bracket close, assign Y equals to A and B and module. Now don't panic, I am not asking you to memorize every keyword yet. Instead, let's ask our three questions. What hardware exists? And function. What does it do? It produces the AND of A and B. How is it connected? A and B enter, the logic processes them, Y comes out. Now the interesting part, what does this code actually become? Imagine I give this code to a synthesized tool. The tool doesn't say, okay, let me execute line 1. No. It asks what hardware does this description represent, and it can infer an AND logic function. So mentally, Verilog AND relationship, hardware logic. And visually, A and B. Why? This is the moment I want you to remember. Code is describing the hardware. This is the core idea of HDL. Let's go one step deeper. We wrote assign y equals to A and B. What does this tell us? A and B are inputs. The AND operator represents the AND relationship. Why is the output AND? Because this is simple combinational logic. There is no clock, there is no memory, there is no register, there is no wait for the next clock. The output depends directly on the current input. So if A equals to 1, B equals to 1, Y equals to 1. And if A equals to 1, B equals to 0, then Y equals to 0. And that exactly what an AND gate does. So we have successfully gone circuit idea, Verilog, hardware description. Now I want to save you from one of the biggest mistake beginner make. They see module, input, output, assign and module and immediately start memorizing definition. Module means this, input means this, assign means this. That's okay eventually. But if you memorize syntax without understanding hardware, you will forget it. Instead, module, think, this is my design block. Input, output, think, these are my external connections. Assign, continuous combinational relationship. This way, you are attaching syntax to a mental hardware model much easier. Now, let's move from one AND gate level to a real engineering workflow. Suppose a company wants to build a digital system. They don't start by writing random Verilog. First comes specification. What should the system do? Then Verilog RTL description express the design. Simulation check whether behavior is correct. Synthesize, convert, synthesizable RTL into implementable hardware. What hardware can implement the design? And eventually gate level hardware and finally FPGA or ASIC. So the simplified flow is specification, Verilog, RTL, third is simulation, fourth is synthesize, then implementable hardware, then last is FPGA, FPGA oblique ASIC. Keep this flow, you will see it repeatedly throughout VLSI. Let's imagine you are an RTL engineer in an actual company. Your manager say we need a digital controller. You don't immediately start soldering gates. You first understand the specification. Then you create RTL description. Then you simulate it. You find bug, you fix them, you simulate again. Once you are confident the RTL behaviors correctly, you synthesize it. Then the design tool generate a hardware implementation suitable for the target technology. That's why Verilog is so powerful. It allows engineers to work with extremely complex digital system using a structured description. Simulation versus synthesis. Now, two words you are going to hear again and again in VLSI. Simulation and synthesis, don't mix the map. Simulation asks, does my Verilog behave correctly? Synthesize asks, what hardware can implement this description? Think of it like this. Imagine you are designing a car. Simulation is like asking, does the car model behave correctly? Synthesize is more like asking, how do we actually construct the machine that performs this design? Different question, different purpose. Simulation is mainly for verification. Synthesize connects synthesizable design intended to hardware implementation. And here is something important. A Verilog description can be useful for simulation, but that doesn't automatically mean every construct is suitable for synthesize. That's why we as an engineer need to understand behavior and hardware implementation. Later in the course, we will constantly ask, okay, this code works in simulation, but what hardware does it create? That's the professional mindset. Let's expose some common mistake. Mistake number one, thinking Verilog executes like C or Python. It doesn't. Mistake number two, memorizing syntax without predicting the circuit. Huge mistake. Mistake number three, reading code without asking what hardware it represents. Whenever you see code, stop. Ask what circuit is hiding behind these lines. That one question will save you a lot of confusion later. Fix always translate code to hardware. Remember this code hardware. Now let's switch into RGPV exam mode. These are the questions you should absolutely be ready for. Question number one, what is HDL? Hardware description language, a language used to describe digital hardware. What is Verilog? Verilog is a hardware description language used to describe digital hardware and its behavior and structure. How is HDL different from a conventional programming language? Programming language primarily describe executable instruction. HDLs describe hardware. Simulation versus synthesis. Simulation verifies behavior, synthesis determines an implementable hardware structure from synthesizable design description. These are classic viva level concepts, so don't just watch this video, try answering them without looking and be prepared these questions by yourself because this will be an important question in RGPV exam. Now let's connect this to industry. Imagine you join an FPGA design company. Your job might be an RTL engineer. RTL engineer, you may spend a lot of your day writing Verilog or system Verilog. But the best engineer aren't the one who can type is its syntax fastest. There are the ones who can look at the specification and think what hardware should exist, then how should it behave, how should I describe it, what hardware will synthesize procedure. That's the skill we are building in this playlist, not just Verilog hardware thinking. Okay, before we finish, I want you to remember only three questions. What is Verilog? A hardware description language. Why do we use it? To describe and design digital hardware efficiently. Does it execute like normal software? No, it describes hardware behavior, structure for tools. That's the foundation. Now there is a mini challenge. No cheating. Look at this. Given what I have given to you, assigned y equals to A and B. Before looking at the answer, draw the hardware. Does this need a clock? Is the output combinational or stored? Do comment in the comment box. So the first question is, what hardware do you see? And logic. Does it need a clock? No. Why? Because there is no storage behavior here. Is the combinational or stored? Combinational. We are not memorizing. We are translating code into hardware. That's the skill. So the final hardware picture is that two inputs, one AND function, one output, no clock, no register, no memory, just combinational logic. And that's what I mean when I say code hardware. Let's bring everything together. Today we have started with a simple question. How can we describe digital hardware using text? And the answer was HDL. Then we learned that Verilog is an HDL. We learned why we need it because manually describing an enormous digital system would be impractical. We learned that Verilog can describe structure, behavior, and connection. We learned not to think about Verilog exactly like Python or C, and most importantly, we learned to translate code to hardware. Then we introduce simulation. Simulation verifies behavior and synthesize. Synthesize determines implementable hardware. Simulation asks, does it behave correctly? Synthesize asks, what hardware can implement it? And finally, we connected everything to RGPV and industry. But now I have got a question for you. We just said that Verilog can describe hardware, but does every engineer describe hardware in exactly the same way? No. There are different level of abstraction. Think about describing a car. You could say it is a vehicle. That's one level. You could describe engine, transmission, wheels, braking system. That's another level. Or you could go ridiculously deep. This specific component contains these individual parts. Same object, different level of details. Hardware work the same. And that's our next topic, level of design description. We are going to take the same digital system and look at it from different abstraction level. And once you understand that, Verilog starts becoming much easier to organize. So today we have learned what is Verilog, why we need Verilog structure behavior correction. Verilog is not like Python C, code hardware, Verilog design flow, simulation versus synthesis. Before you go, remember one line, don't learn Verilog as a text. Learn Verilog as hardware. If you can look at Verilog and mentally see the circuit behind it, you are already thinking like an RTL engineer. And that's exactly where we are heading. So if you are following the complete RGPV HDL VLSI journey, subscribe now because in the next video we are going to take one hardware design and zoom in and out through different level of abstraction. When you see the same circuit represented at the different levels for the first time, you will finally understand why HDL needs abstraction. If you enjoy this Verilog introduction, unit number 1, RGPV ED302 syllabus, then give thumbs up, share this video with your friends, and thanks for watching. To subscribe the channel.